So let's say we've got a function of two variables, f, x, y, and we've seen that we can take the derivative of f in two directions, either del f by del x to measure how f changes in response to changes in the x variable, or del f by del y to measure changes in the y direction. But then just as in ordinary calculus, we can keep going. So if we differentiate del f by del x with respect to x again, then we get what we'll denote del squared f by del x squared. If we differentiated this, though, with respect to y, then we'd get what we denote del squared f over del y del x. And then doing the same to del f by del y. So if we differentiated this with respect to x, we get del squared f over del x del y, or del squared f over del y squared. So all of these are going to be measuring some kind of acceleration. So as always, this is best seen through examples. So let me work through several examples. So let's stick with the examples we've already worked out, since that way we've already got the first derivatives worked out. So if f of xy is y squared minus xy plus y cos x, then we found that del f by del x is negative y minus y sine of x. So now this gives del squared f by del x squared. This will be negative y cos x, and del squared f by del y del x. This will be negative 1 minus sine of x. Now let's set this off. So del f by del y we found was 2y minus x plus cos x. So now if we do del squared f by del x del y, now we'll get, this will give negative 1 minus sine of x, and del squared f over del y squared will just be equal to 2. And so notice that we got the same answer when we did del f by del y del x versus del x del y. So we got the same answer regardless of which order we differentiated when we did x and y. All right, next let's revisit fxy equals y sine of xy. So here we found that del f by del x is y squared cos xy. And so del squared f by del x squared. So now we'll do the chain rule. So inside we'll pull out a y and we'll get negative y cubed sine xy. And then del squared f by del y del x. Now we need to use the product rule. So this will give 2y cos xy minus xy squared sine xy. Then let's sort of try to block this off here. We found del f by del y was sine xy plus xy cos xy. So if we do del squared f by del y squared, we'll get, this is x cos xy plus, and now we need to use the product rule. So this will be plus x cos xy and then minus x squared y sine xy. And so then we can combine these two terms. So it's 2x cos xy minus x squared y sine xy. Then finally, so let's bring this down here. So del squared f over del x del y. So now we have sine. So that'll give y cos xy. And then here we use the product rule again. So we'll need another y cos xy. And then the chain rule, it'll be minus xy squared sine xy. And again, you can see that we got the same answer for taking the mixed partials of x and y in both directions. All right, here I'm going to do a new example, since the fraction examples that we got into before were pretty nasty and I don't want to differentiate them even further. So let's look at f of xy equals xy plus e to the x over x squared plus 1. So first let's find just the first derivative. So this will be del f by del x is y plus, we have to use the quotient rule, x squared plus 1 squared. Derivative of e to the x is e to the x, so we'll get e to the x squared plus 1 minus 2x e to the x. And del f by del y is a lot simpler, it's just x. Okay, now for the second derivatives, we'll get, so del squared f by del y del x is 1. And again, we'll see that that's the same as taking del squared f by, so if we differentiate with respect to y first and then with respect to x. So then for the other two partials, we'll have del squared f by del y squared is 0. And then the last one is going to be the worst. We'll get del squared f by del x squared equals something over x squared plus 1 to the 4. And then, you know what, let's not even write this out. So it'll be whatever the derivative is of e to the x squared plus 1 minus 2x e to the x times x squared plus 1 squared. So here you'd use the product rule to find whatever ungodly expression that is, and then minus that same expression, e to the x squared plus 1 minus 2x e to the x, but now without a derivative. And then the derivative of x squared plus 1 squared will be, this is getting horrible. I guess we could use the chain rule. So this will be 2 times 2 times x squared plus 1. And then all over x squared plus 1 to the 4th. So I'm not going to expand all that out and see what it works out to, but you could plug that into Wolfram Alpha or something. Now, let me also do an example with 3 variables. So let's look at x squared yz plus cos y squared z. So first let's find the first derivative. So do this f sub x. This is another notation for del f by del x. It's a little shorter. This will be 2xyz, then fy will be x squared z minus 2yz sine y squared z, and fz will be x squared y minus y squared sine y squared z. Okay, now let's find the second derivative. So f xx we can see will be 2yz. f yy will be, so now we need to use the product rule, so we'll get negative 2z sine y squared z, and then minus, so, and then we'll pull out, so this will be minus 4y squared z squared cos y squared z, and fzz will be, so the x squared y goes away, so this will be negative y to the 4 cos y squared z. Okay, now let's try the mixed partials. So f xy will be, so now we differentiate first with respect to y and then with respect to x. So now this stuff all goes away, and we'll just get 2xz. And we can see that's also the same as if we did differentiate with respect to x first and then with respect to y, although we sort of get there by a shorter route. Then f xz, so this is with respect to z first and then with respect to x, that'll give 2xy. And again, we see that we get the same thing if we did with respect to x first and then with respect to z. Or let's do fyz, this will be x squared. Then now we have to use the chain rule again, so minus 2y sine y squared z, and then minus, that'll be, I guess, 2y cubed z cos y squared z. And if we take, if we did with respect to y first and then took with respect to z, we can see that, yeah, we get an x squared here, and that, yeah, we'd again be getting the same thing. And then just by way of illustration, we could keep on going. So we could do, let's say, f xxx, or del cubed f over del x cubed. This we can see as 0. Or f zzz, this will be y to the 6, or sine y to the 6 sine y squared z, or like here we could take f zxy is equal to 2x, is equal to f zyx again. And that's the same as if we took f y x z, or f, y, z, x, we're always getting 2y in that case. Or 2x rather. So whenever we do these mixed partial derivatives where we're taking with respect to different variables, we keep getting the same answer no matter which order we do the differentiation in. This is no coincidence. So we have the following theorem. So let me just state this for a function of two variables. If x, xy, and its derivatives fx, fy, fxy, and fyx, these are defined throughout an open region and are continuous at a point AB contained in that region. Let's write that. Contained in that region, then the fxy, where we differentiate first with respect to y and then with respect to x, evaluated at the point AB, is equal to fyx, where we take the order of the derivatives in the opposite direction. So there are counterexamples to this where if the derivatives are discontinuous at this point, then you can get different answers depending on the order you take the derivatives in. So there's examples of that in the textbook, but this is sort of pathological behavior. In most of the cases that we're interested in, you can take the derivatives in any order and you'll get the same result. And then this extends to higher variables like we saw, like f x x y would equal f x y x would equal f y x x, or f x y z would equal f z x y, and so on. So for all the different permutations of the variables.